Did you know astronauts on the International Space Station actually age a little slower than people on Earth? Like, actually slower. And here's the wild part. The same effect is corrected inside your phone every single day. Yeah, your phone. Before you think this is some sci-fi nonsense, let me ask you something. If time can slow down, how does the universe decide whose time slows down? And even more confusing, why don't we ever feel it happening? Take a guess and comment it, even if you're not sure. I'll get to the answer later in the video. Most of us grow up believing time is the same for everyone and everywhere. 1 second always equals 1 second. That's what even scientists believed for centuries. Newton literally thought time was like a giant universal clock, ticking the same way across the entire universe. But Einstein's special theory of relativity tells a very different story. Time doesn't actually flow the same way everywhere. Einstein's idea was simple but shocking. He said that time and space are linked together, and the speed of light is the same for everyone, no matter how fast you're moving. To make that work, time itself has to change. Meaning, time actually depends on how you move and where you are. So, how does that work? Why does it happen at all? Imagine this. Picture a straight highway. You're driving a car at 60 kilometers per hour. Next to you, another car is also moving at 60 kilometers per hour in the same direction. From your view, that car barely seems to move. It feels like you're both almost standing still. Now, a third car passes you at 120 kilometers per hour, going in the same direction. From your point of view, that car feels like it's moving 60 kilometers per hour faster than you. From the car next to you, it feels exactly the same. But from inside that fast car, things flip. From her point of view, you're the ones moving backward at 60 kilometers per hour. So who's really moving and how fast? Everyone is moving, but the speed you measure depends on your point of view. There's no single universal answer. Speed is relative, and time works the same way. Now, take that same idea and let's push it to the extreme. Imagine this. You stay on Earth. Your friend gets into a spaceship. That ship moves insanely fast, like almost the speed of light. After some time, they come back. You are older. They're noticeably younger. No time machine, no magic, just speed. The faster you move through space, the slower you move through time. And here's the weird rule of the universe. Everything is always moving through space-time at the same total speed. So, if you use more of that motion moving through space, you get less left for time. That's why time slows down. It turns out there are two main ways time can change. The first one happens when you move really fast. Moving fast messes with time. And scientists actually tested this using extremely precise clocks. They built incredibly precise atomic clocks, accurate down to billionths of a second. Then they did something simple. They kept one clock on the ground, and the other one was flown around the planet in airplanes. When they brought them back together, they didn't match. The moving clock was behind, not broken, not malfunctioning. Time itself had passed differently, and the atoms inside the clock were literally vibrating slower. That's when people realized, oh, this is real. But speed isn't the only thing that affects time. There's one more factor that messes with time, and it has nothing to do with motion. It's gravity. Stronger gravity slows down time. The closer you are to something massive like Earth, the slower the time passes for you. So, a clock on Earth's surface ticks slower. And on a satellite, it ticks faster. This isn't some tiny meaningless effect. GPS satellites have to correct for this constantly. If they didn't, your location would drift by kilometers every single day. So yeah, relativity is literally why Google Maps works. All right, remember the question I asked you at the start of the video? What decides whose time slows down, and why doesn't anyone feel it? Here's what's really going on. In relativity, there is no universal clock and no correct time, meaning nothing special is being chosen. There isn't some master clock in the universe to decide whose time is right and whose is wrong. Every object, you, me, an astronaut, a satellite, carries its own clock called proper time. Time passes differently based on the path each one takes through space-time, like how fast it's moving and how strong the gravity around it is. That combination, your speed and your gravity environment, is what physicists call your path. Now here's the interesting part. When time slows down for you, everything slows down together. Your watch, your heartbeat, your brain signals, your thoughts. Nothing gets left behind. So, from your own point of view, nothing feels off. Nothing feels delayed. Nothing feels broken. Time feels completely normal because for you, it is. That's why astronauts don't feel slower in space, and people on Earth don't feel faster. Everyone experiences their own time smoothly without noticing anything strange. The difference only becomes visible afterward when two clocks that took different paths, different speeds, and different gravity are brought back together and compared. Only then do we notice one clock has experienced slightly less time than the other. This is the part that often trips people up, because once you really understand this, something surprising follows. Time travel to the future is already possible. Astronauts are doing it. Satellites are doing it. Even you are, just extremely slowly. If humans ever travel between stars, they might come back to a future Earth that aged way more than they did. So, next time you look at a clock, just remember, time isn't something that flows the same for everyone. It's personal, and the universe doesn't care how strange that feels. Thank you for watching till the end. I really appreciate you being here. If you found this video interesting, feel free to drop a like. Maybe share it with someone who might find this video interesting. Until next time, take care.